I'm going to tell you what little I know of this guy. He went to MIT and Stanford, these two kind of small sort of third-tier schools. You may or may not have heard of them. I'm not sure. So I'm not quite sure about this guy's pedigree, but he'll have to do. On a recent sweep of European universities, I think I visited 7 of them over about a 5-day period back in May. Georgia's university and Georgia's team really stood out. I visited some of the top universities in France, Switzerland, Germany, and the work down there was just really first rate. They're not only doing testing, they're building some tools that are solving some really important problems. So I expect that through our office in Zurich and through mine up here in Kirkland, we're going to be doing a lot of work with Dr. Candia and his team, hopefully hiring some of the students and supporting some of this research. So I'm going to hand it over to George in a second, but I want you guys to send me any feedback from this so I can get it to George. Obviously, ask questions as we go through, but if you have any specific interest in any parts of this work, please pass that feedback to me, because I'm kind of taking it on myself to coordinate a lot of our outreach with universities. So having said that, George, all over to you, and hopefully we'll be a kind audience to you.
Well, hopefully not. Thanks, James, for the intro. Can people hear me if I speak from this distance? Yes. Oh, James can hear me, and he's probably pretty far away, so that's pretty good. So, well, good afternoon. Thank you for inviting me to give this talk. As James said, a lot of the work we do is very much applied. We like to pick our problems from the real world. I myself have spent a fair amount of time in industry, and if I can't justify the work we're doing with a very clear problem, then I don't feel comfortable. So I will share today some perspectives on software reliability. These are some of the thoughts are half-baked. Some of the thoughts are baked a little more. And my goal is that with the feedback that we'll get from you, we can refine this further and make sure we're working on relevant problems. And so the problem that we're looking at today in the present is that a lot of when it comes to the reliability of the software we use, there's little choice but really take it on faith. And together with my students, I'm trying to help fix that. And I'll illustrate with a kind of a classic example, which I think we've all been through. Say you administer a bunch of home PCs, and you need to install a device driver for the network card used in these PCs. Okay? What you need to do is you take this driver, which is really just a bunch of machine code that was written typically by some teenage programmer that you've never met, and then you install this machine code, this unknown machine code inside your operating system, and you allow it to run at the highest privilege level. And when I talk about acts of faith, this is an example, right? This is what I mean by an act of faith, because if this random teenager walked up to you on the street and asked you for the keys to your car, you probably would not give your keys to this teenager. But somehow you're willing to give this code the keys to your computer, which probably is more valuable than your car. But we don't necessarily think of it in these terms. So what is the state-of-the-art defense that we have today for this kind of things? Well, it's a pop-up window, which you can read what's on it, and I'm sure you've seen this quite a number of times, which is a warning, and it says, well, you might screw up your system with what you're about to do. And here are 2 options. Do it anyway, or don't install the software. So it's really your choice. Either way, you can't safely move ahead, because if you don't install the software, you can't use the hardware. Now, wouldn't it be great if instead of this, you could go to some independent website, upload the device driver, tell the website what kind of software you just uploaded, and then just push the test button. Okay? And then automatically the service explores all the paths, looks for bad behaviors, things like race conditions, data corruption, deadlock, and so on. And then for each bug found, it allows you to download, you just click on this button, and you can download an executable replay trace. And this executable replay trace is basically a proof that the bug is real and it's reproducible. So this would be nice. Now, this is not science fiction. We actually developed a technique that can do such automated testing of proprietary drivers. I will not talk about it in a lot of detail today. Whoa, I just did something wrong. In any case, this is good to repeat and to get the message even better. So anyway, what I clicked away was a reference to this paper that explains how we combine an automated test generation technique called symbolic execution with virtualization and dynamic binary translation to provide this kind of completely automated testing of device drivers on x86 binaries. Now, for those of you familiar with symbolic execution, you know that this allows you to explore the execution paths through the code and then look for bad behaviors along these paths with no human assistance, right? And that's important. And if you'd like more details on this work, I'll be happy to talk about it during the Q&A session. Now, I should mention that this RTL 8029 example that I'm showing you here is actually one of the most popular network device drivers that has been shipping with Windows for, I think, over 10 years. And it is Microsoft certified. Yet we did find these bugs. These bugs shown here are true bugs found in this driver and a bunch of other Microsoft certified drivers as well. So this is an example where installing drivers constitutes an act of faith, because we know they have these bugs, at least now we do, yet we still use them. And I know what the problem is. The problem is that the bottom of the screen is cut off. So I don't know if there's something I need to do about that, or the AV folks can do something about it, but we're missing the bottom part of the slide. Okay, so moving right along, I venture to say that the software industry is really a faith-based industry to a large extent today. So programmers kind of write code, and the best of us also do write some tests, but essentially we write code and then kind of hope for the best. Users take it on faith that the vendors have performed thorough testing. And third, there's really no way for consumers to assess the reliability of a piece of software before they use it, buy it, install it, anything like that. So this is a very strange industry. And unfortunately, this isn't working out so well, because if you look at, there's a survey which is down here, which has found that over the last few decades, the density of bugs has kind of stayed the same. Bugs per 1,000 lines of code. And depending on whom you ask, well, it's anywhere from 1 to 10 in production quality software. But at the same time, what's happening is that the volume of code is increasing exponentially. So constant density, increasing volume, this means that we have more and more bugs floating around. And so clearly, this faith-based approach is not working. So what we need is a disruptive technology that will enable us to improve software quality by an order of magnitude. So we're attacking this in two ways. First, we're working on developing practical techniques for automated testing and debugging. So there's a lot of research on this topic, but very little of it actually is practical, meaning it runs on large-scale software. So the first part is practicality. The second one is, what I'd really like to do is offer reliability as a service. And what I mean by this is make software testing and debugging as easy as webmail. It should be inexpensive, fully automated, accessible to everyone. And then if we provide this as a service, we want to develop the techniques that can actually harness the resources of massive commodity clusters to actually provide this service very quickly, make it very fast. As I said, we're huge fans of automated test generation techniques like model checking and symbolic execution. Unfortunately, these techniques do suffer from path explosion. We're all familiar with that. The number of paths through a program is typically exponential in the size of the program. And so these techniques, if you run them, especially if you try to run them on large pieces of software, they bottleneck on CPU, run out of memory quite quickly before actually you can get any decent coverage on more than a few thousand lines of code. And as it turns out, these are also very hard to parallelize, so we can't just throw cluster hardware at the problem. Our goal is to make these techniques scale and accessible. So what I'd like to do today is talk at a high level about the 4 reliability services we have in mind, and then dive in depth into one of them, namely automated debugging. Now, in terms of services, I've already shown you an example of testing as a service for device drivers, the one with the website. And such a device could really empower consumers to test the software they use before installing it. So we think of it as the home edition of testing as a service. Beyond this, developers would also like to use this. So we think of reliability service software to developers, both in terms of testing, the developer edition, and automated debugging. And finally, a reliability certification service, which would act as a sort of Underwriters Labs for the software industry. Now, whereas the home edition used a web browser to interact directly with the service, developers would use the IDE as an interface to this service, so that while they're writing their code, the service does continuous testing in the background of that code, continuously pulling code from the developer, exercising the paths through it, and then checking for that desired properties hold along these paths. Now, continuous testing, as we are all aware, is very useful because it catches bugs as the software is being developed, right? So you want to catch these things early on because that's when they're cheap to fix, and that's when everything's still in your head because you wrote the code. Now, if we do this as a service, then it can become a lot more powerful than anything we could do on our workstations, right? Because the cloud, the cluster, has much bigger resources, so we can test much deeper. We can look for much more systemic properties along these paths. So my hope is that this form of continuous testing that actually runs in the background will one day become as indispensable as, for instance, automated spell checking right today in word processor. Right, as you type your word, well, if it's the wrong word or it isn't spelled right, it tells you. So hopefully we'll have something like that. We have taken one first small step toward this. We have a preliminary prototype running on EC2, but there's still a lot of work left to do on this of cluster-based continuous automated testing. The reason we are investing effort in this is because if we get to the level where this is just as quick as sort of on-the-fly spell checking, then we as programmers can spend more time thinking about system-level properties and less about sort of the low-level stuff that can be automatically checked for, right? So we use the human brain for stuff that humans are really needed, and whatever machines can do, we delegate to machines. Another reliability service helps debug deployed code, namely code that is out there running in the field, and then you get bug reports from it, right? In a sort of service-oriented setup such as Google, this may happen in a slightly different form, but for things like platforms, Android and Chrome OS and so on, you would imagine having this situation as well. So this service would take a bug report and information about the program that is being debugged and send that over to this debugging service, which will then produce what we'll refer to as an explanation for the rest of this talk. It's basically it walks you through how that program could have exhibited the bug shown in the report. And then this explanation is actually something you can plug into a classic debugger and just, like if you're in GDB, just say, run or next, and you can just step through it and you see the bug happening without you having to think about how it could have come about. So we built a system that synthesizes this kind of an explanation for bugs entirely automatically, based solely on a bug report. And in the second part of my talk, I will describe in more detail exactly how we do that. And now for the final service, we want to build a certification service. This provides an objective assessment of a software product's quality. You can imagine this service of going out there and thoroughly testing software products using these automated techniques, publishing the results, and thereby enabling consumers to differentiate products based on their reliability, something you cannot really do today. At most, you can read in like a CNET report or something like that. And the same way, you no longer buy a car that has not undergone official crash testing. I hope you will soon refuse to use software that does not carry a quality certification, perhaps something like that if we have our way. So software companies compete on measurable things. They compete on performance because it can be measured through benchmarks. They compete on features because you can check them off a list. Now certification services will hopefully add another measurable thing to that companies can compete on, which is reliability. And at the moment, we haven't actually built this system, but we're gathering support to provide it as a public certification service. So we've seen 4 reliability services: testing for home users, testing for and debugging for developers, the certification service. Before I move on to the second part of the talk, I should ask the question: is this just about slapping a web interface on top of existing techniques, and say symbolic execution or model checking? And the answer is no. These techniques still have substantial challenges to overcome. Not only is path explosion a problem, but if you run some of these, you will see that constraint solvers bottleneck. You end up spending a lot of CPU time constraint solvers. They blow up in terms of memory. If you want to put this in a cluster that uses commodity interconnects, anytime you have to ship state from one node to another, it's expensive. So this isn't a trivially parallelizable problem, unfortunately. I wish we could do it with MapReduce. The world would be a better place. So the proof that this is a hard problem is that after more than a decade of research on the topic, the parallel model checking community has still, to my knowledge, not come up with a cluster-based parallel model checker that can actually work efficiently. So let me show you how we tackle some of these problems in the case of automated debugging. I will describe first how we cast the problem of debugging as a search problem. Then I will show you how we combine static analysis with symbolic execution to help developers debug their code. And then I'll show you some results. And to motivate this, let's see what is the state of the art in debugging standalone programs. If you work on your computer and you use Windows or any other reasonably large piece of software, you may get one of these, which is kind of the system hangs. You can then sort of end application, and then you might get something like this, which says, well, now I have prepared a bug report, some automated way of telling the vendor what happened, and I'm about to send it off. And then you click send, and there's the bug report produced by the software itself. And I'm not picking on Microsoft software. My Mac happily gets into these situations all the time. Now, once you have this bug report, it will be sent off to some big debugging factory where humans kind of toil away in cubicles and racking their brains trying to figure out how that bug report could come about. How did the program go from the start state to the end state that is captured in the bug report? And the classic approach is really to try over and over again to reproduce the bug, hope to catch in the debugger, look at the code, try to understand how it happened. And what we want is to really try to automate that. Okay? Now, to get a little more specific, what is it that typically we need in order to reproduce one of these problems? Well, it'd be nice to figure out what the program inputs were or could have been for that program to hang or to deadlock or to crash. How it interacted with the environment, say what network packets it might have received, what system calls it made, and what the results were, and what was the thread schedule. And if you can guess these three things about what happened in production, then you have a pretty good chance to actually reproduce the bug on your own workstation and then figure out what's broken. Now, in terms of research, the state of the art is to record many of these things in production, and often virtual machine-based approaches are used for this. And the goal of these tools is to reproduce the buggy execution exactly as it happened at the customer site. But of course, you have to pay the cost of performance overhead in production. Now, clearly the classic approach is not working. We have direct experience of that, and surveys, for instance, this fairly recent one from Microsoft from 2008 shows that a lot of bugs take months to diagnose. Now, what I do want to point out is that I expect things to actually get worse. Modern software is increasingly parallel, and the hardware that this software runs on is increasingly parallel as well. So the number of possible executions that can occur out in the field is growing dramatically. And while our brains aren't necessarily growing at the same rate. So there'll be more and more diverse executions, which will make it more and more difficult to debug. So there'll be more guesswork. And as a result, they'll take longer to find the fixes and push them out. So the problem is that programmers get turned into sort of bug detectives. And then these mysteries that they need to solve are becoming more intricate as the software becomes more complex and the hardware is becoming more parallel. So it'd be really nice to automate this detective work. And we developed a technique called execution synthesis that, similar to what I've shown you earlier in terms of the debugging service, will take a bug report and a program and then produce this explanation that you can plug into the debugger. And we can do this with no runtime tracing, no program modifications, and no runtime overhead. And we've tried it out for real on some database software, web servers, etc. So let's sort of dive now into how we actually do this. I've been talking about bug explanations, and this tool produces bug explanations. These are really three sets of items. As I was mentioning, program inputs, the interactions with the environment, and this is mainly the interaction with the environment happens through libraries and system calls. So these are the things that we would like to be able to produce. And the thread schedule, and all of these that led to the field reported bug to manifest. Of course, the bug report does not contain these things. The bug report just contains the end result. So how do we get them? Well, the idea is to reconstruct them. Okay. Obviously, something doesn't quite compute here because you can't, there's some information loss. But the key insight that actually makes this possible is that as a programmer, we don't really need to replay the exact same execution that occurred at the customer site. What we need is some feasible execution that exhibits the same bug. Okay, someone didn't like what I said. And it's upside down. Is there anything I can do to the blue button? Voila. I should always have a blue button with me. That seems to work. So we don't need to replay the execution. We need to replay the bug. And to replay the bug, there's a number of possible executions that can do that. And with execution synthesis, we want to synthesize one such execution. That makes the problem a lot simpler. And this makes sense because the developers really want an explanation of the bug, not necessarily of how it actually ran at the customer site. In fact, you may not even be able to run the same execution that occurred at a customer site because it's environment dependent. Right? So if you see how the bug manifests, then you can see the causality chain that causes the bug. And this eliminates the guesswork that I was referring to earlier. So you don't have to do any more detective work. And if you can deterministically observe the buggy behavior in a debugger, then you can employ classic techniques to fix it. You can do step-by-step execution, data structure dumps, look at the program state, and so on. So this is the key enabler of execution synthesis, this distinction between replaying the execution and the bug. So one way to do this is to think of debugging as a search problem. There are many paths through a program, often infinite number of paths, and we want to find a path that takes from the start of the program down to the actual bug. So the natural thing to do is to explore all the paths through the program, and then when you hit the bug, you found the path you need. Of course, when you have an infinite number of paths, there's somewhat of a problem with this approach. But for now, suspend your disbelief, and let's look at an example. This code here is a snippet from SQLite. It's a real bug. It's a deadlock bug. And for those of you who can read the code real quickly, you'll see that there's a possibility that this lock is acquired out of order. So you do a lock M1, M2, and then if you unlock M1, you will lock M1 after having locked M2. So you have a lock inversion relative to other thread that may be going through a different path. So that's how you can deadlock. So what we might want to do is, let's say we execute the first statement, then we get to this branch, and this branch, in terms of paths, creates two possible paths, right? One for the then branch and another one for the else branch. And so we can capture this as shown here. We put the condition in a box, and then we say, well, we have a true branch and a false branch. Then we move on. This is another if condition, and this also now branches the execution, and it will branch both this part of the execution and this part of the execution. Okay? And then we move along, and we get to the next predicate, next if branch, which itself will also split the branch, will split the execution, and so on and so forth. So this is one way to explore all the paths, right, very systematically and exhaustively through the program. And this is at the heart of symbolic execution. Now, obviously, the problem here is that we just had 3 branches, and this tree now already has 2 to the 3, 8 possible paths. So this blows up. So this naive approach conceptually works. It will work for small programs. It will not work for real programs. And I've just shown you the example of the number of paths being exponential, but if you think about the thread schedule as well, that adds another dimension of complexity to the problem. So even though the approach won't work, let's try to build on it. Okay? What we need is to really be clever about how we do this search. How, maybe we can explore parts of the tree and not worry about the other parts of the tree. So we can solve this search problem more efficiently. And if we think of it as search, we have to now more precisely define what the goal of this search is. Okay? So far I've talked about bug reports, but really what we want is this end state. And a bug report, this has to be extracted from the bug report. So the goal, more formally speaking, is a tuple, B and C, where B is a basic block, which is where the bug actually manifested. So for instance, if your program crashed, the basic block where or maybe even the program statement on which it crashed. And C is a condition that needs to hold for that bug to actually occur. So for example, if you have a crash due to a null pointer dereference, this is the simplest possible case, then what you need is the program counter of the instruction that actually caused the null pointer dereference, and the condition is that pointer is null. So you can see how this, you can easily pull this out of a core dump. A little more complicated if you go to a deadlock. There, you need the program counters of every thread involved in the deadlock, and you need to capture the cycle between the mutexes that were held by the threads. In the case of a race condition, it becomes even nastier because you can have a race condition that occurs over here, and then it causes a problem down here. What we need is the program counter or counters of the detection site where the actual problem was observed. And then, if, for instance, it was caught by an assert, we would use as the condition the negated assert. So you see how for different classes of bugs, you have different B's and C's. ESD, which is the tool that implements this technique, extracts these goals automatically for crashes, hangs, wrong output failures from the core dump, and also for bugs in external libraries. So now that we have the goal, this tuple B and C, how do we find a path to it efficiently? So remember, the simple naive approach is to do this sort of exhaustive search and then hope to hit the goal. This blows up. So instead, execution synthesis uses static analysis to work backward from the goal and identify what we refer to as intermediate goals. These form a skeleton that will then guide the forward dynamic analysis to search from the start state to the first intermediate goal, then from that goal to the next one and the next and so on. And these searches actually constitute an envelope for the paths, the potential paths that lead to the goal. Okay? So this static analysis part is really crucial. And so this is because it trims down the search space considerably. Okay, so what we've seen so far is that we've cast the debugging problem as a search problem. The naive search does not terminate, so we break down this search into a few into smaller searches. So now let me dive deeper into how we do the static analysis and the dynamic analysis. So we need to look for these intermediate goals, these red dots, and we work backwards from the goal, this B and C. So the first step is to use the control flow graph and look for what we refer to as critical edges. Critical edges are edges in the control flow graph, such as this one, which must be traversed by any path that reaches the goal. So here you can see that in order to get to this goal, you have to go through that edge. There's no other way. So we find these critical edges. And you see how working backwards, you would find these edges. Now, the branch that corresponds to the critical edge will, first we have to decide, obviously we're taking the true branch or the false branch, which is easy to do because you know based on the edge what that is. And then for each variable involved in the condition inside that branch, we find sets of instructions further up that are reaching definitions for those variables inside the condition. And then we look for combinations of instructions from these sets that would give the branch condition the desired value. Okay, so this is kind of a data flow analysis for which we use the data flow graph. And then, based on this, we can construct the intermediate goals, which are really instructions with static guarantees that if you execute it, then the critical edge would be followed. Right? And then, of course, these basic blocks that contain the reaching definitions, you can mark them as intermediate goals. And if you have more of them, then you mark the intermediate goal as a disjunction. Again, we can go into more details later if you'd like. So let's see an example. There's, again, our SQLite code. And here we established this as a goal because, when this deadlocked, well, there was a thread that tried to acquire M1 and it couldn't, and it was stuck because some other thread held it. And then if you look backwards, you'll see that for that lock M1 statement to actually be feasible, you need this condition to hold true. And part of that condition holding true means that the mode variable has to be set to mod y. And then you go backwards and you look where is the mode variable set to mod y. And at this point, you have an intermediate goal. Now, it's a very simple example, just to illustrate the idea. As you can probably intuit, there's a lot more analysis that goes into this, but this is fairly standard static analysis. So we actually, we didn't invent this. Let's see the blue button. Oh, awesome. I'll take this remote with me. This is great. So once we work backwards to find these intermediate goals, we just hop from one to the next in the forward dynamic analysis. How does the forward dynamic analysis work? Well, for those of you who do not know about symbolic execution, I will sort of tell you in 30 seconds what the idea is here. When you run a program, you can run it with concrete inputs. Pass it an actual integer, number 5, or some string, or something like that. Or you can pass it what are called symbolic inputs. These are inputs that could take on any value, and that's okay. I'm enjoying this. So these take on any value, and you can think of them as unconstrained inputs, right? So something that is, that you pass it value 5, it's constrained to be 5. I can pass it some value that is unconstrained. It could take on, say, any integer value. By doing that, we can then explore every branch instruction independently of what that value is, and then remember along each path what is the constraint that has to hold on that particular variable or those variables along that path. So, for instance, down here, see on this true branch, what we know is that mode is constrained to be mod y, and idx is constrained to be 1. So those are called path constraints, and each branch condition imposes a constraint on the variable involved in that condition. Now, as we're building this tree, remember, we don't want to necessarily explore the entire tree all the time. Actually, it would be a bad idea to do that. So at any given point in time during the exploration, we have this frontier. Right? These are unexplored states of the program, and the question is which state to explore next. If you choose smartly, you will only explore the states that will get you to the goal, right? So if you had sort of an oracle that told you exactly what to choose, you just go straight through the tree and find the goal and you're done. So what we want to do is sort of, well, that's pretty hard to pull off, but let's see if we can get close. And the key, we use a variety of heuristics, but the key metric in execution synthesis is this notion of proximity, which is a tight lower bound on the number of instructions required to reach the goal from the current place in the program. Proximity is computed based on the control flow graph. And given a current location in the program, for instance, if the goal is inside the same procedure or the same function, it's kind of easy. You just choose the shortest path from where you are to there in the control flow graph, and that is a tight lower bound. So you use that as a heuristic for how close a given state is to the goal. If the goal is outside the procedure, it becomes a little more complicated because there's various ways you might reach the goal. For instance, you might return from the current function and return from the next one up and then follow it through, say, the second function up the call stack. So there, to compute the proximity heuristic, we actually compute this distance metric, the proximity metric from where we are to the nearest return instruction, and then apply this computation to the other functions in the stack. So it's basically how long will it take me to return, and then once I return, how long will it take me to reach the destination. And this proximity heuristic then guides us in which state along that frontier to choose. And think about, you realize this is simply an optimization, right? This is not a correctness guarantee of any sort, but it helps guide the search towards the states that are closer to the goal and keeps us away from the ones that go off, into other subtrees that we're not interested in. So we use this heuristic, we choose the states, we search through the tree, and once we found a path, then there's something for us to do. Now, how do we know that we have found an interesting path? Well, the program counter now equals the B in our goal, right? And the constraints along the path on the variables are consistent with the C condition in the goal. So for instance, if we want a pointer to be null, then if the C condition, if the constraints along the path allow the pointer to be null, then it means that it is indeed possible to reach that location with the pointer being null. So I don't get too far from the mic, but say we got down here somewhere. Actually, let's see. Yeah, so down here would be the actual goal in that code example we had. Then you just go backwards up in the tree, take the path constraints along each edge, put them in a big conjunction, and feed this to a constraint solver. And the constraint solver will then come up with assignments to the various variables involved that will make the path constraints along that path true. And that solution will give you the inputs and will give you the values required by conditions such as this one, where you make, for instance, system calls or library calls. What value has to be returned to enable that particular path? And you're pretty much done if this is a single-threaded program. Now, the problem is, well, with multi-threaded programs, which is more and more the case in practice, we also need to synthesize a thread schedule because certain sequential paths may not interleave the way we would like them to interleave. So real quickly, the idea here is that if we have two different threads, we want to interleave the threads such that they follow the desired path to the goal. And we use for this search, we use heuristics that are specific for each type of bug. And to illustrate, let me give you the example of deadlocks. Think of the schedule, which basically says, how the threads interleave. Think of that as yet another symbolic variable. And what we're trying to do is solve for that symbolic variable. And this schedule is kind of a bit vector with each bit saying that, at this particular opportunity for preemption, there was a preemption or there wasn't a preemption. So just on-off. And this long string of bits is a symbolic variable. Now, if we just did the search blindly, of course, it would take forever, but we can use clues from the core dump. In the case of a deadlock, for instance, the call stacks are a very, very powerful clue because we see the threads that got stuck in the deadlock, what calls they made. And the interleaving of these calls tells us, right? Because we see what locks they hold, we see where these locks were acquired, and so this tells us where would be interesting preemption points to put in. More generally, when you're trying to find paths to explain deadlocks, you really just need to put preemptions before and after the synchronization calls. Because if you preempt anywhere before a synchronization call, it's kind of all the same, right, in the absence of race conditions. So if you have no race conditions, then it doesn't matter where you've been preempted. The bottom line is that someone else may get to that synchronization call before you do, some other thread. So we use this heuristic. We use the call stacks as clues. And putting this together with what you've seen on the previous slide, we now have the inputs, the values received from system calls that came out of the constraint solver, and the thread schedule that we actually modeled as this bit vector, and we actually found the particular values for these bits. So now what? We have this stuff. Ideally, we have the original binary of the program, and we would like to connect to it with a debugger and just see the thing happen, see the problem happen. So to do this, we have a custom shim library which plays back the right inputs that were found with execution synthesis, intercepts all the system calls, and feeds the synthetic return values. And you can imagine how this, sort of builds a shell around the program and really makes the program makes the program have the illusion that things are happening exactly in the right way for that bug to be triggered. And for the thread schedule, for instance, in the case of deadlocks, this shim library would intercept all the POSIX thread calls and feed do the right timing, hold threads up, to let others get ahead and so on, to enforce the synthetic schedule. And this schedule shows up as a set of dependencies between instructions in different threads. It just says, this instruction has to run before this one, and then this one before this other one, and so on. So the program has no idea. It is not talking to the real world. It's behaving just as if it would behave if it were in the real world. And we can see that in the debugger. Now, I'm insisting on this original binary story because, as you well know, build processes in the real world are fairly complicated. And there's also flags, and there's also things that happen to the code in the build process. And then what you really want, it's the binary that experienced the failure. And you may do analysis on the source code, but because of some optimization in between, you actually can't find an explanation because the explanation is actually in this process. So we want to be able to make this really be visible in the binary itself. So this is how execution synthesis does this detective work that I mentioned. What we did was we used backward static analysis to help the forward symbolic execution stay within the bounds of what's strictly necessary. We found an execution and we played it back using this shim library, and this playback is 100% deterministic because any source of external non-determinism is eliminated with this shim library. Well, does it work? We built a prototype that works today mostly for C programs, but there's no technical reason why it cannot work for other kinds of programs. And here are some of the results. We like to work on real systems, so we looked at a few of them. SQLite is an embedded database that is used in a variety of products. HawkNL is a networking library. GHTPD is a web server. And then these are a bunch of Unix utilities. And then we went out and looked for actual bugs reported against these real systems. And we said, well, can we take the bug report and actually come up with an explanation automatically? I should also mention that we wanted to span a wide range of sizes. So this actually spans 3 orders of magnitude. SQLite is about 100,000 lines of code. And it goes all the way down to some of these little Unix utilities. There are a few hundreds of lines of code. So we'll see how this affects running time and so on. The kind of bugs we found, we focused on the ones that felt a little more interesting. Was, for instance, this one in SQLite was the deadlock bug that I showed you earlier. So it results in a hang. This is another deadlock bug in HawkNL. This one actually was a security vulnerability. It was a buffer overflow that would eventually cause the web server to crash. And then most of these are segfault type of bugs. And so we ran ESD, our prototype, on these, and the execution synthesis time was pretty fast. The longest one took on the order of 3 minutes. And the reason it's fast is because the heuristics really help the search. So this is not a guarantee that for all the bugs it will always be this fast, because these are heuristics. So there are corner cases where it might take longer. We are actually ourselves are trying to understand a little better how these heuristics work. But for these bugs, it worked out quite well. Another thing I should point out is that it is, for these kind of tools, it's quite important that they work for shared libraries as well, not just for standalone programs. So for instance, SQLite, I mentioned it's an embedded database. So this is something that is used in Firefox, it's used in the iPhone, it's used in Mac OS X, it's used in Nokia Symbian OS, it's used in Skype, it's used all over the place. So all of these programs out there might deadlock if they tickle that bug that I just showed you. So you fix a bug in a shared library, and then you have impact on a much wider range of programs. Now, we're researchers. One of the things we do is we compare to the existing state of the art, and so my practical mind says like, well, the state of the art is some super duper programmer. Well, okay, hard to compare to that, and probably would win. I mean, it's hard, you know, in a few minutes to. I mean, it takes a few minutes just to read the bug report. But there are no tools, to my knowledge, there are no tools that can take a bug report and figure an explanation out for you. But what we did was we took 2 research tools that were recently published 1 or 2 years ago. One is the CLI symbolic execution engine, which is used as a bug finding tool, and the chess bug finding tool, so CLI doesn't work for multi-threaded programs, and chess is a tool that finds bugs in multi-threaded programs. So we kind of put these 2 things together to build this super tool that finds, you know, looks for bugs in programs. So we compare to that. Now, this is not a fair comparison because they're bug finding tools. So they're not really focused on finding a path to a certain place. But as I said, there's no tool that I know of that does that. So this is the closest we could come. And by doing the comparison, we'll actually see what the benefit is of these optimizations that we put in. So this is a graph that shows along the y-axis on a log scale, you see the time, the path synthesis time. Basically, the time it takes to find a path. In the case of ESD, it makes sense to call it synthesis. In the case of the other tool, not necessarily so. And then we ran it on the various bugs that I showed you earlier. And in blue, you see ESD. And the red and the yellow are, or green, whatever that color is, are 2 different strategies for this super tool that I was referring to. That was the combination of CLI and chess. Okay, so we want to see how the search strategy influences things, and so we tried 2 different strategies. One is plain DFS, and the other one is a random path, which is actually the best performing one in the original systems. And what you see here is that in 1 hour, which is what we have up here, this tool, this super tool, was unable to find a path. I mean, in some sense, it's not really surprising because the number of paths is so great. So it ran for an hour, it still hadn't found a path, and then by comparison, ESD was able to find the path, as we've seen earlier, in 3 minutes or less. But then we said, well, okay, we've got to give this tool a chance, this super tool a chance. So what we did was we took the ls utility, which is a small Unix utility, and we introduced synthetic bugs. We actually put in some null pointer dereferences in a bunch of places, and that was findable by this tool, this CLI-chess combination. And ESD also found those bugs, luckily, but it did so in an order of magnitude less time. So these heuristics and the static analysis that helps guide the search does actually pay off. So to summarize, I've shown you how we take a bug report, feed it into this execution synthesis story, use a combination of static analysis and symbolic execution to produce an explanation which consists of a code path, the program inputs, and the thread schedule. And this can then be fed into your classic debugger and replayed. And remember, the key insight that allowed us to do this is the realization that we don't have to replay the execution that occurred in the field, but just replay the bug, right? And any execution that evidences the bug will do. So we cast the debugging problem as a search problem for this B and C. And this technique is really one of the, this is behind one of the services that I was talking to you about earlier, the automated debugging, which is targeted at developers. Now, so we're getting to the end of my talk. In closing, I want to emphasize that we really think that if we are to reduce bug density by an order of magnitude, which is what the goal was that I mentioned at the beginning, we really need to engage both technical and non-technical forces. So on the one hand, we must develop techniques that automate testing and debugging, such as the one that I showed you today. and make them work for real software, not just for toy software. And on the other hand, we really need to find ways to enable free markets to promote competition based on reliability. Because otherwise, well, who will really care? I think that economies of scale allow us to make automated software testing inexpensive and accessible to everyone. If we provide this as a service, you realize there's a lot of redundancy in testing that can be taken advantage of to actually make this a feasible proposition. And then if we drive the cost of testing down, that will level the playing field and allow even the smallest programming teams to match the testing resources like the ones that you have here. You have massive clusters, vast amounts of very smart people. Even the little guys can have access to that kind of test quality. So maybe in this way, we'll one day say goodbye to this sort of faith-based approach to software reliability. And the day we do that, I'll be a happy man. So thank you for your attention, and I will be more than happy to take questions.
It's a good idea. Cluster the people.
Yeah. I have a question. Question, George. If someone else isn't asking one already.
Go ahead.
Okay. So it seems like you're running this on kind of native compiled binaries. Have you any experience of doing this with web applications running inside a browser and what that would take?
We haven't looked at that yet. And, I guess I could. That's a Kirkland door, I guess. So I can speculate that I actually think that it may be easier from the point of view of the technique, because having access to the actual code, if we're going to do this on a JavaScript type of web app, then that would probably work. We'd have a lot richer information that we can leverage in this kind of analysis. But at the same time, and I was sharing this with some people I was meeting earlier today, we've had to do tremendous amounts of engineering to actually get this to work on real code. I mean, it is, there's all these little things that you have to take care of, which are not sort of pure research. They are just stuff to get it to work. So I'm saying this as a caveat to my answer for JavaScript, because who knows what would have to solve once we sort of, take a look at this kind of web apps. But at least from a conceptual point of view, it seems that it would be advantageous to try those out. We haven't yet, but hopefully we will.
Okay, thanks, George. Hey, we're getting thrown out of our room up here, so we're going to have to sign off.
Okay, play it safe.
Thank you.
Yes.
Has the work you've done given you any insights into, from the development side, like what design patterns would make software, where the software would make it easier to do this kind of analysis?
Yes. So the question is whether the work we've done has taught us anything, has given us any insights into what developers could do to make the code more debuggable or easier to test or anything like that. Is that?
These kinds of techniques that you're trying to develop more applicable to their.
Or to make our techniques work better with their code. And I think that is a great question. There are many things that can be done, and the truth is that I'm not a programming languages person or a static analysis person. I hail from an operating systems background, but as I understand, the community has introduced many clever ways, for instance, to annotate one's code that would help this kind of tools. Clearly, if you don't use pointers, things would be so much easier. You don't have to worry about pointer aliasing. So there's a lot of work out there. I can't even represent it accurately in 2 minutes. But what we've tried to do is sort of push it to the extreme and say, well, what if we are to maximize the productivity of the programmer and say that, well, you, the programmer, don't have to do anything. You just have to think about how you write your code and just write the best code you can and let the tools do the rest. I think the most practical solutions are probably somewhere in between, where you do inform the tools a little bit about what it is that is happening, or at least, you provide invariants. You can, the more assert statements you put in the code, the easier it is for the tools to, understand, okay, so if there's no way I could have gone down this path because, this assert tells me I couldn't have been there. So yeah, all these things help. There was, I think, a question in the back. Yes?
You said you have a heuristic about considering context switches only happen before or after the text.
Mm-hmm.
So does that assume the programmer using indexes correctly?
So the question is whether our heuristics described in the case of Deadlocks, the heuristic where we said we introduce preemption points before and after mutex operations, whether this assumes in any way that mutexes are used correctly. Is that correct? So the answer is no, it doesn't make that assumption because so by using mutexes correctly, you mean acquiring them in a certain order or, not doing double releases, double acquisitions.
You're assuming that there's something special about the critical section. The programmer, if there's another critical section of the code, the programmer will protect it all.
So that's good. So in that case, we talk about what I would call a race condition, where because you have something that should be a critical section not be protected by mutexes, then you actually may access shared state in a way that really depends on the scheduling. The output may be sort of an uncontrolled effect of whether this thing comes before or after. And the heuristic I described works in the case of there being no race conditions. You have very correctly pointed out that in the case of race conditions, this is problematic, and the tool actually does do a dynamic race detection, largely based on the eraser algorithm, whereby during the search, it looks for opportunities for races. And if there are parts in the code where there could be a race, it actually explores those alternatives as well. So the complete way to describe this would have been to say that we introduce preemption points before and after mutex operations, as well as in locations that on the search path we actually find opportunities for races. So that's a way to augment this. And there are also, if you are looking, for instance, for a bug that's caused by a race condition, then you can employ other algorithms for race detection to do that. Yes?
So it looks like the building of the explanation leverages static analysis a lot to figure out how to get there. So I was wondering, is simply having a bug report, filtering out a lot of false positives your static analysis is going to give you? Like, wouldn't it be beneficial just to run static analysis on the binary and see that there's a chance for race condition here and fix that before it went live? Or is there just too many false positives?
That's a wonderful question. The question is whether we can actually think of the bug report as something that trims out a lot of the false positives that static analysis would find if we were to just run the static analysis on the program itself. And so the bug report kind of gives us clues to eliminate all sorts of possibilities that a static analyzer may find that are not true possibilities. Is that a correct representation of the question?
Yes, that's my question.
Okay, so that's a wonderful question because that's, in some sense, exactly what happens if you do not have. So you could run the static analyzer just as part of your testing process, and typically you will get a lot of warnings. Now, depending on which tool you use, how complete and sound it is, etc., you typically get a very large rate of false positives. Especially the larger the code base is, you use pointers, things get really crazy. And the bug report tells you, I'm only interested in those, say, races that occur on the path to this end state. And I'm not interested in any of the others that you might find. Right? So that by itself, because now it sort of imposes a restriction on the paths through this entire space that you're interested in, static analysis can be a lot more focused. Because static analysis aims to be complete, so it tries to reason about all the paths. But given an end state, many of these paths cannot get there. So the bug report conceptually filters out many of the false positives. Now, how to cross that conceptual bridge and actually bring it into a tool, that's probably what we've done with execution synthesis. I think that's very perceptive. It's a way to really leverage that information. Any other questions here or in the ether? Yes.
So I know that there's some companies, like most notably Microsoft, that they sign like drivers and other things,
Mm-hmm.
and they enhance the quality. So, like, do you know what the process is, sort of state of the art in the industry, for saying that something is certified to be installed on the computer?
A great question. What is the state of the art in industry with respect to certifying software? For example, Microsoft assigning various pieces of software that it ships that undergo a certain certification process. So first of all, let me say Microsoft does have some extremely advanced tools to do both static analysis and symbolic execution. Some of the greatest work that we build on as well actually did come out of Microsoft and Microsoft Research. And to give you an example, let's talk about, for instance, the I think it's called the Windows Hardware Certification Program or something like that, where you write a device driver and then it's actually put through a testing process at the end of which, if the driver sort of emerges successfully, Microsoft will put its stamp of approval, and when you install that driver, you will not get that pop-up warning that I showed you. Right? So that's an example of this. There has been very interesting work. In particular, there's a tool called SLAM, which was published, I'd say, about 3 years ago or so, that uses model checking to test device drivers. And at the time, this was a very advanced tool because it worked for actual C code, actual driver code. One of the reasons for which our tool, DDT, found bugs in Windows certified drivers is that to make the approach that SLAM has practical, it does have to cut some corners. And those corners that you cut are unexplored paths. And to give you an example, SLAM will take the driver and test it in isolation of the rest of the system around it. So the entire Windows kernel API has been modeled, actually manually, people actually wrote models for the various calls that can be plugged into the model checker. And these models, by necessity, are incomplete. And it actually took 3 years to model the entire API. We do not rely on modeling in the DDT tool. We actually run everything natively. We run the drivers inside Windows, inside this virtual machine. So the technique is slightly different. But these tools are very powerful. I don't know what the statistics are about how many bugs they do find, but they're not complete. And I think the certification is really not a guarantee. It's not something that says the software is guaranteed to be free of bugs. It just says we put it through our stringent test process, and it's not the random teenager who wrote the code that you have to trust. You have to trust our Microsoft's test process. And well, as we all know, there's no perfect testing. So, despite it being very stringent, there's still things that fall through.
But I mean, can we ever get to where we're just not? How like we want to move beyond trusting that random programmer,
Mm-hmm.
and then at some point we have to move to trusting the test suite, right? If you're saying the software is great about it.
So the follow-on question is, won't we always have to actually trust the test suite in order to assert that something is free of bugs? And I think that is true. Ultimately, what a bug is will have to be stated by someone. The kind of bugs we looked for and that I used in this talk are things that everyone would agree are bad things. I mean, who would argue that a deadlock is an intended behavior? Well, nobody. You know, a null pointer dereference. These are bad things. No one has to formulate them formally. No one has to argue about whether they are not a bug. So there's nothing to trust. But ultimately, you will have to trust the definition of a bug. In the certification service that I presented, our intent is really to run these automated tools and look in a first stage for this kind of lower level bugs and provide you guarantees that, for instance, this device driver is free of race conditions. There are no race conditions whatsoever. There's no deadlocks. There's none of this, none of that. So these are guarantees that the current tools cannot provide. They don't scale. And further down the road, you remember there was this developer edition where you would actually write, you know, you have your IDE and you're writing up your code and it's testing it in the background. One of the things I didn't talk about is that I'd like the IDE to allow you, as you write the code, to specify properties of interest. So while you're writing the code, you realize, oh yeah, I could write an assert that, you know, would check a certain property. Now asserts are very local type of properties, but you can imagine more global properties. About how many locks are being held or how many threads are running at a time. And then if you had an easy way to specify that, you, the programmer, that gets pushed to the service and it can be checked, and then you can actually get a guarantee that that property will hold along all paths. And these kind of guarantees amount to formal proofs, which are still very difficult to do, and I don't think the certification service will be able to do, it will be able to provide formal proofs of this sort. But we'll be able to provide guarantees for certain types of bugs, for, you know, when the code operates under certain conditions, and so on and so forth. Yes.
For example, this auto-debugging example there, we have a very specific bug, for example, recording the program counters and the state of the variables and different things. Now, for consumers that may be looking for some more basics, like what you're talking about, this software doesn't have risk conditions, those kind of things. So, how can you generate all these cases for their rating requirements?
I see. So I will try to rephrase the question, and then you'll tell me if I'm going down the right path. So the question is whether, in the case of testing as a service for consumers, how would this service be able to test for properties that the consumers are interested in? How would the consumers communicate these properties to the service? Because for the developers, you know, we just talked about writing asserts. We talked about, you know, execution synthesis takes the goal. Well, how do consumers do that? Is that correct?
So it's more about the technical side. So how we come from this assert for requirements to the input to this service. Because for this automatic debugging service you're talking about, we have very specific inputs.
Mm-hmm.
Now, how do we translate from an assert to all these kind of example steps?
The kind of properties to look for. How do we decide what properties to look for just based on asserts in the code? It's a good question. We haven't thought about going from asserts to properties that are looked for by the end user version of testing as a service. But what we envision for that is something close. For now, we can look for the kind of bugs that everyone agrees upon that are bad things. And I also think that having something like Wikipedia style or null style contributions of such predicates by people like yourselves, we might say, oh, here's something that's really important for device drivers not to violate. There's a particular type of kernel call that shouldn't be done after some other type of call or so on. So I can imagine sort of this open environment of contributing to a database of properties that are important. In a first stage, I think, there's just a small set of properties that obviously, are still being violated. So once we sort of eradicate those, there'll be more and more sophisticated properties you could put into this database. And perhaps, these, if there's, say, a commercial entity that provides this testing as a service, they might tap into this open database, or maybe this database becomes a competitive advantage. They say, oh, we have a better database than the other company that offers this. And personally, I'd like to see an open database that everyone can contribute to. But I think that would be one way to go about it. We haven't thought about automated techniques. I'm sure they exist, but I would just speculate about it at this point. Anything else? All right. Well, thank you all, and thank you for the great questions.